Okay, so in this video we're going to derive the ballistics equations. Um, so let's start with the origin. So this is going to be the position from which the projectile originates. So this is going to be the origin. And the second point is going to be the target. And let's say our projectile starts at the origin and moves with the initial velocity u, or initial speed u, and it is going to go in this direction. So it's going to make a parabolic trajectory until it hits the target. And let's say the vertical distance between origin and target, we're going to define that as k. And the horizontal displacement is going to be the h. And the initial angle at which the projectile moves is going to be theta. Okay, so we have, in 2 dimensions, we have 2 equations of motion. We have x as a function of t, which is u times t times cosine theta. And we have y as a function of t, which is u times t times sine of theta minus 1/2 gt squared. So there is no friction in this case, so you have to figure that out on your own, but there is a gravitational component. Okay, so using the first equation to solve for t, we get t is x divided by u cosine theta. And replacing this in the second equation, y of t, we get y equals, let's just write it out, u times sine theta times t, which is x divided by u cosine of theta, minus 1/2 g x squared divided by u squared cosine squared of theta. Okay, so notice that we have some terms we can simplify. So we have u on top and bottom, and sine theta divided by cosine theta is tangent of theta. So y becomes x tangent of theta. And copy this second term. Okay, so we can replace y and x with k and h. So y was k, k times h tan theta minus 1/2 g h squared divided by u squared cosine squared theta. Okay, so now we're over here. Okay, so we can define this term k divided by h, which is going to be a. So define a as k divided by h, which becomes, basically we just cancel out one of these h's. So this becomes tan theta minus 1/2 g h divided by u squared cosine squared theta. Okay, so now we need to define another term, b, which is going to be basically just this part here. So basically the strategy is to get everything in terms of z, which is cosine of theta, and all the other constants, we can just hide them in these a and b terms. So this becomes negative, or sorry, positive. 1/2 gh divided by u squared. And of course, we define z as cosine of theta. Okay, so now we can simplify. Okay, so with this equation, if we divide both sides by h, then we're going to have k divided by h, which is tangent of theta minus 1/2 gh divided by u squared cosine squared of theta. So this is just a equals tangent of theta minus b divided by cosine squared of theta. Okay. And as you recall, tangent of theta is actually sine divided by cosine of theta. So let's put that back. So sine of theta divided by cosine of theta minus b divided by cosine squared of theta. Okay, so so we know that sine of theta is the square root of 1 minus cosine squared of theta, right? And okay, let me just look here. Yeah, okay. Oh, also we can just start using z's to, so we don't have to write out cosine of theta each time. We can just use z. Okay, so let's say a is the square root of 1 minus z squared divided by z minus b divided by z squared, right? So this is just this equation here. Okay, so now we can multiply both sides by z squared. So a times z squared becomes z times square root of 1 minus z squared minus b. So this is this equation here. And I think if you're paying attention, you know where I'm going with this. Essentially, we're going to be using the quadratic formula at some point. We just need to put everything in terms of x and then have our constants. So this is not the x that's here. Then this is just a placeholder. So in fact, x is going to be z squared if you look at this equation here. But okay, let's get there. So we're at this step here, and we want to move everything to one side. So okay, so basically we're just gonna okay, let's just do it. Okay, So z squared, 1 minus z, z times the square root of 1 minus z squared minus b minus a times z squared is equal to 0, right? Which means that, okay, this is probably kind of roundabout way of doing it. I'm just moving stuff around, but okay, so z square root of 1 minus z squared is going to be b plus a times z squared. Okay, what does that mean? That means that we can square both sides, right? So we can have z squared times 1 minus z squared is going to be equal to b squared plus 2 ab or ba times z squared plus a squared times z to the fourth. Okay, and so we can distribute z to both sides. So this becomes z squared minus z to the fourth is equal to b squared plus 2ba z squared plus a squared z to the fourth. Okay, and now we can move everything to one side, so the other side is 0. So this becomes z squared minus z to the fourth minus b squared minus 2ba c squared minus a squared z to the fourth. Which is equal to 0. Okay, so now we need to factor out all the z squared and z to the fourth terms. So, okay, I think we're over here now. Okay, so now if we combine all the z to the fourth terms, we get minus a squared minus 1 times z to the fourth plus, let's see, plus 1, oh, sorry, 1 minus 2ba times z squared. And then we have the constant term, which is minus b squared, all equal to 0. So now we have a quadratic equation. And basically, okay, so basically this is a quadratic equation in z squared. And let's say, I don't want to use x again. Let's use capital X. Let's say capital X is equal to z squared. So by quadratic formula, we know that capital X is going to be minus b plus or minus square root of b squared minus 4ac, all of that divided by 2a. And these small ABCs are just these coefficients. So this guy, let me just draw that here. So this guy here is our, oh crap. Can I do that? No, okay. Well, anyway, this term is just our small a, this term is our small b, and this term is our small c. And when we use the quadratic formula to solve for x, then we're going to get two solutions. We're going to get minus b plus square root of all this stuff divided by 2ac, and then minus b minus all this stuff. And basically, what that means is you can have two thetas, right? So as you recall, z is cosine of theta, which means that we can solve for theta. Let me do that here. Oh, okay. Can I? Here, okay. So theta is just going to be the arc cosine of z, which is going to be the arc cosine of the square root of x. And the two values of x, the plus and minus one, are just going to be the, so you can have two trajectories, right? You can have one which uses the smallest possible theta, and then you can have another one which goes way up here, but also hits the same target. And as you move further away from the origin, both of these solutions are going to become 45 degrees, until at some point beyond that you won't be able to reach the target no matter what theta you use. So that means that there's a natural range which is a function of your initial velocity or your initial speed and the gravity. So basically you have to shoot the projectile fast enough in order to reach a specific distance. Okay, well, this is not a very elegant solution by any means, but I'm pretty sure this is accurate because this is the code that I use, and I tested it. Okay. And also you can do a little sanity check here. So let's say we assume that k equals 0, which means that the target and the origin are on the same plane, the same horizontal plane. And that means we can simplify some things. So for instance, a, which is defined as k divided by h, becomes 0. And let's see, what is this equation here? This is just this equation. So this is 0, this is going to be minus 1. This is going to be 1 because a is 0. And this is just going to be, so okay, there's a minus sign in here, right? So this equation becomes z to the fourth minus z to the squared plus b squared. And if you rearrange those, then okay, so you move this guy to this side, and then you divide everything by z squared, and this becomes 1 minus z squared equals b squared divided by z squared. And as you recall, 1 minus cosine of theta squared is sine squared of theta. So sine squared of theta becomes b squared divided by cosine squared of theta, which is sine theta equals b cosine of theta, which is square root both sides. And so we multiply both sides by cosine of theta. And there's an identity which says that sine of theta times cosine of theta is just 1/2 sine times 2 times theta, which is equal to b. Okay, so how is this a sanity check? Well, this is just a much simpler equation. So if you don't trust all this stuff here, then you can just use this very simple equation, and you can test that fairly easily. But yeah, I wish there was a more elegant solution, but this is basically it. And okay, so another thing that you have to worry about is not just the curvature due to gravity, but also the leading the target, right? So let's see if I can find that here. So let's say the target is moving, right? And by the time your projectile reaches this position, the target will have moved. And if we assume that it moves at a constant velocity, then we have to correct for that. So here the capital T is just the time that it takes the projectile to reach the target. But this assumes that we're moving on a constant speed, so we're not doing this whole curvature thing. So this is just an approximation. Because, okay, so let's say you have a choice of using either this trajectory or this trajectory, right? So this trajectory is going to take longer, right? So assuming that that you use the same speed, but you just angle it higher, this trajectory is going to take longer. And in fact, you can use this equation here because the horizontal velocity is constant, right? So you're going to have two t's in this case, one for this case and one for this case. And you can use those to calculate how long it takes the projectile to reach your target. And you just move the target along its velocity by that amount. Okay, so this is not perfect, obviously, because if you have a very fast target, then you're going to have to also look at the different angles, right? So let's say the target is moving straight towards you, right? That's going to be very different than the target moving away from you. So maybe I'll do a different tutorial on that later. But if the target isn't that fast compared to the speed of the projectile, then this is a pretty good approximation. Okay, well, I've rambled on long enough. So there you go. Here's your derivation. And I might do a second tutorial later to discuss the leading the target calculation. Okay, that's it.